This is the first part of the answers for problems from chapter 21. And the first set of problems has to do with resistances in series and parallel. The one thing to remember about resistances in series and parallel is it's exactly the opposite as capacitors in series and parallel. So what you learned about the capacitors, that is that capacitors in parallel, you just add up the total capacitance, and capacitors in series, you use the fractions. It's the opposite. That is, series resistances are added up, and parallel resistances use the fractions. The other thing I'll point out is in a series circuit, as I said, the total resistance is going to be equal to the resistance, the sum of the resistances, however many resistances you have. Secondly, the current in a resistance is constant throughout the circuit. So at any point in the circuit, the current is always the same. And the voltage drops across each resistance as it goes past, but the sum of all the voltages across each resistance has to add up to the total voltage. And for parallel circuits, as you know, 1 over RT is equal to 1 over R1 plus 1 over R2, etc. The voltage is constant throughout, and the total current has to equal the current in each resistance that's in the circuit. So these are the principles of series and parallel circuits that I want to make sure y'all remember. Now, with that intro, let's do problem number 2. Problem number 2 says, what is the resistance of a 100 ohm, a 2500 ohm, and a 4000 ohm resistor if they're connected in series and if they're connected in parallel? Okay, so the first one's in series. As we said, the total is going to be the sum. So it's 100 plus 2500 plus 4000. And so that's going to equal 6600 ohms of resistance. Now the parallel is 1 over the total is equal to 1 over 100 plus 1 over 2500 plus 1 over 400, which is equal to 0.01, excuse me, that's 1 over 100, plus 0.0004, which is 1 over 2500, plus 0.00025, which is 1 over 4000. If you add that up, you get 0.01065. And then so that's 1 over RT. So RT is going to be the reciprocal of this, and the reciprocal of that number is 93.9 or 94 ohms. All right, number 4. Number 4 says a 1800 watt toaster, a 1400 watt electric frying pan, and a 75 watt lamp are plugged in the same outlet of 12 amps and 120 volts. When they're plugged in the same outlet, then they're in parallel. What is the current drawn by each device? Okay, so you have a house current, which is 120 volts, and the current is 15 amps. Now the question is, what is the current drawn by each of these? Well, in order to find the current, first of all, you have to find the resistance. Well, you can do it one of two ways. You can say that the current has to be proportional to the resistance in each appliance. And the resistance of each appliance is equal to the voltage squared over the power. Okay, so for example, for the first one, which was 1800 watts, that would be 120 squared over 1800. The second one, which was 1400 watts, that's going to be 120 squared over 1400. And the third one, which was the 75 watt bulb, that's 120 squared over 75. And each of these is the resistance. This is 8 ohms, this is 10.3 ohms, and this is 192 ohms. And so the total resistance is, if you take each of these and add them up like this, and I'll do the shortcut for the math here, the resistance here is going to be 4.4 ohms. So the total resistance is 4.4 ohms. Now, if the total resistance is 4.4 ohms, and in a parallel circuit the current is constant, okay? And so that means that the voltage is constant. So the current in the first appliance that has a resistance of 8 ohms is 120 over 8. For the second one, it's 120 over 10.3. And for the third one, it's 120 over 192. So this one is 15 amps. This is 11.65 amps. And this is 0.625 amps. And then the second question is if you plug this into a fuse that's 15 amps, will it blow? Well, it's well over 15 amps total. So yes, indeed, this thing will blow the fuse. And that's how you can tell when something like that's going to happen. Number 6. Number 6 states, referring to figure 21.6, calculate P3 and note how it compares to P3 found with the 2 example problems in this module. Okay, now I went back and looked at P3, and in P3 the voltage is 48 volts, or in example 21.6 I mean, and the the resistance in R1 was calculated out at 24 ohms. The resistance in R2 was calculated out at 96 ohms. And so the total resistance, since these were in series, these two were in series, the total resistance was, adding those two together was 120. That's 24 plus 96. And the total current in that area is going to be equal to V over R, which is equal to 98 no, I'm sorry, I'm getting ready to put it down wrong. It's 120 over 96, which is 0.400 amps. And so the power is equal to, for that P3 is going to equal V times I, which is equal 48 times 0.4. Now, if you're having trouble following this, make sure you have the example or figure 21.6 in front of you while you go through this, because that's where I'm getting a lot of these numbers. Now, the second part of this says repeat this when the resistances are in parallel. All right, so what you have to do is repeat this calculation with the resistances in parallel. And if you do that, that means that the total, 1 over the total, is going to be 1 over 24 plus 1 over 96. So that RT, when you do the math here, comes out to be 19 0.2 ohms. And then the calculation IT is now going to equal 48 over 19.2 or 2.5 amps. And then the power is equal to V times I, which is equal to 2.5 amps times V, which is 48, or 120 watts. So when you put these in parallel, you see that you use a considerable amount more power than if you put them in series. Now, 8 says, referring again to figure 21.6, calculate P3 and note, wait, I just did number 6 and talked about it as if it was number 8. So I hope you can go back and look at that. Sorry about that. So this is the answer to number 6, where number 6 is giving us 48 volt battery and a 24 to 96 ohm resistor. Find the current and power when they're connected in series and in parallel. And that's what I just did here. Now we're working on number 8. And I'm sorry that I got that confused. Okay, so for number 8, if you assume that P3 is the power used in R3 in the picture, in R3 in the picture, which is 13 ohms, will be divided into V3, which is the voltage drop at R3. Now make sure you have example 21.6 in front of you. So you're assuming that P3 is the power that is used by R3, and R3 is 13.0 ohms. And then you divide, and you have to understand that V3 is going to be the voltage drop at R3. Okay. So if you're looking at the example, the total voltage is equal to 12.0 volts. Okay. And it shows you that V1 is 2.35 volts, the voltage drop at the first resistor. So the total voltage is going to equal V1 plus, V1, let me write that again. The total voltage is going to equal V1 plus V at P. Okay, and VP includes R3. This is why I put that in there. So that means that VP is 12 minus 2.35 or 9.65 volts. And the V2 and V3 are in parallel, so V2 is equal to V3 is equal to 9.65 volts. And the reason we did this is that's what you need to calculate P3. And P3 is equal to V squared over R, which is equal to 9.65 V3 squared over R3. 9.65 squared over R3, which is 13, which is equal to 7.16 watts. Now the other question here is, find the total power supplied by the source and compare it to the sum of the powers dissipated at the resistors. Well, the total power is equal to the voltage total times the current total, and that's going to be 2.35 times, or that's the current, times 12. And if you do that, it's going to be 28.2 watts. The power at the first resistor is going to be equal to this 2.35 times, squared over 1 amp, or 1 ohm, resistance, This is V squared over R. And so it's 2.35 over 1, or 5.5 watts. And P2 is going to equal 15.5 watts. So if you add P2 plus P1 plus P3, you get the total. In other words, what they want to show is that the power used at each resistor, the total, if you add those up, it equals to the total power used in the circuit. Let's do one more. Actually, we're going to skip number 9 and go to number 15. And 15 starts where we talk about EMF. And if you have a single cell EMF is equal to 1.54 volts, and you want to know how many cells you're going to have to use to get a 9-volt battery, you just take the 9-volt battery and divide it by the EMF per cell, and that will tell you that you need exactly 5.84 cells, which obviously you can't have a 0.84 of cells, so you need a total of 6 cells. And the actual voltage you're going to have, terminal voltage you're going to have, is going to be equal to 6 times 1.54. So instead of exactly 9 volts, you're going to have 9.24 volts. Now the last part of this question is discuss how internal resistance in series connection of cells will affect the terminal voltage. The internal resistance causes a loss or an inefficient. The internal resistance of a battery causes inefficiencies in a battery, and so it will decrease the available voltage that you can have.